know that mechanical energy is required to run many machines. But major sources of energy, like fossil fuels, can generate heat energy. A device that converts heat energy into mechanical energy is called a heat engine. A steam engine, diesel engine, and a petrol engine are some examples of heat engines. In any heat engine, a small quantity of matter, usually called the working substance, acts as the system. For example, water is the working substance in the case of a steam engine, and a mixture of fuel and air is the working substance in the case of a petrol engine. The working substance undergoes a sequence of processes that finally leave it in the same state in which it started. Such a process is called a cyclic process. The schematic representation of a heat engine is as shown. In each cycle, the working substance passes through the following main processes. First, it absorbs heat from a hot reservoir maintained at a high temperature. Let the temperature of the hot reservoir be T1 and the heat absorbed by the system be Q1. After absorbing heat from the hot reservoir, the working substance does some work on the surroundings and converts part of the heat absorbed into mechanical energy. Let the work done by the system be W. At the end, the working substance rejects some heat to a cooled reservoir, maintained at a low temperature, say T2. Let the heat rejected to the cold reservoir be Q2. Again, the working substance goes through the same cycle. To get the required mechanical energy, the working substance goes through the same cycle repeatedly. In a cyclic process, the initial and final states of the system are the same, and hence there will be no change in its internal energy. That means delta U is equal to 0. But according to the first law of thermodynamics, we have delta Q is equal to delta U plus delta W. Therefore, for a cyclic process, delta Q is equal to delta W. As the heat absorbed and heat rejected by the system is Q1 and Q2 respectively, delta Q is equal to Q1 minus Q2. Since the work done by the system is W, we get Q1 minus Q2 is equal to W. Let this be equation 1. The efficiency of heat engine is defined as the ratio of the work done by the system to heat absorbed. Efficiency eta is equal to work done by heat absorbed, which is equal to W by Q1. But as per equation 1, W is equal to Q1 minus Q2. Therefore, eta is equal to Q1 minus Q2 by Q1, which is equal to 1 minus Q2 by Q1. Let this be equation 2. If Q2 is equal to 0, then the efficiency of the heat engine becomes 1 or 100%. This means, if we can construct a heat engine which converts the total heat it absorbed into work, then its efficiency is 100%. But in practice, it is not possible to construct a heat engine with 100% efficiency. This is not due to any technical aspect, but because of the second law of thermodynamics, which we will study in subsequent modules. There are two different types of heat engines. One type is the internal combustion heat engine. Diesel and petrol engines are examples of internal combustion engines, and the other type is the external combustion heat engine. The steam engine is an example of an external combustion engine. Let us discuss a 4-stroke petrol engine. This is also called an Otto engine, as it was first invented by Otto in 1876. The engine consists of a steel cylinder with a movable piston. The piston is connected externally to a crankshaft. There are two valves fixed at the top of the cylinder, I and E. Valve I is used to allow fuel into the cylinder, and valve E is used as an outlet of burnt gases. S is the spark plug used to produce electric sparks. The working of the petrol engine can be described in the following 4 steps. In the first step, a mixture of petrol vapor and air enters the cylinder through the inlet valve I. During this process, the piston moves down, and this is called the intake stroke. Now, both the valves I and E are closed, and the piston moves up. The upward motion of the piston compresses the mixture of fuel and air to a high pressure, resulting in an increase in the temperature of the mixture to about 500 degrees Celsius. This motion of the piston is called the compression stroke. At the end of the compression stroke, the spark plug produces a spark and ignites the fuel. Burning of the fuel generates a very high temperature and pressure and pushes the piston in the downward direction. This is known as a pass stroke, because this stroke provides a large amount of mechanical energy. Now, valve E is opened. The piston moves up and pushes the burnt gases out. This is called the exhaust stroke. In every cycle, the piston repeats all these 4 strokes. Hence, the engine is called a 4-stroke engine. Now, let us see how a steam engine works. It consists of a main cylinder with a movable piston. The piston is externally connected to a crankshaft, which in turn is connected to a flywheel. The top portion of the main cylinder has 2 ports, called the front port and back port. In a chamber adjacent to the main cylinder, a valve is allowed to slide. The sliding valve is positioned in such a way that at any given time, both the ports are either in the open state or in the closed state. At the top of the chamber, there is a steam inlet and a steam outlet through which steam is allowed to enter or leave the cylinder respectively. The flow of steam into the main cylinder is controlled by the movement of the valve. Now, let us study the working of the steam engine. Since the required steam is generated in an external furnace, this is called an external combustion engine. Steam at a very high temperature is allowed to enter the chamber through the steam inlet. Let us start with the position where the sliding valve is in front of the front port and allows steam to enter the main cylinder through it. As the steam enters the main cylinder through the front port, it pushes the piston backwards. During its backward movement, the piston pushes the used steam out through the back port. Slowly, the valve starts moving backwards and the steam in the cylinder expands and pushes the piston further backwards. As the valve moves further backwards, the steam flows into the main cylinder through the back port, and it starts pushing the piston in the forward direction. The piston pushes the exhaust gas through the front port. Again, by moving the valve forward, we are back at the initial position. The repeated movement of the piston makes the flywheel rotate. Note that the movement of the sliding valve is controlled by a separate gear system. The movement of the valve is used to control the steam that enters the main cylinder and the speed with which the piston oscillates. Now let us understand the working of a refrigerator or a heat pump. The schematic representation of a refrigerator or a heat pump is as shown. A refrigerator is a device that takes heat from a cold reservoir, and after some external work is done on it, it releases some heat to a hot reservoir. Assume that the working substance receives heat energy Q1 from a cold reservoir at a temperature T1, and after W work is done on the system, it rejects heat energy of Q2 to a hot reservoir at a temperature T2. The coefficient of performance alpha of a refrigerator is defined as the ratio of heat taken from the cold reservoir to the work done. Alpha is equal to Q1 by W. But as per the law of conservation of energy, Q2 minus Q1 is equal to W. Therefore, alpha is equal to Q1 by Q2 minus Q1. Let us understand the working of a refrigerator. The working substance in a refrigerator is called a refrigerant, and in many refrigerators, ammonia is used as the refrigerant. The main parts of a refrigerator are the compressor, expansion valve, and heat exchanging pipes. The liquid refrigerant, while passing through the heat exchange pipes located inside, absorbs heat and evaporates. The vapor, which is at a low pressure, then enters the compressor. The compressor does some work on the vapor, and as a result, the pressure and temperature of the vapor increases substantially. The high-pressure hot vapor then passes through the exchange pipes located outside and releases heat energy to the surroundings. During the process, the hot vapor condenses to liquid. Then, the liquid refrigerant passes through the expansion valve, and due to sudden expansion, it cools further. In this way, the refrigerant absorbs heat from the cooler inside regions of the refrigerator and releases it to the hotter outside regions. Earlier, you learned that the efficiency of a heat engine eta is equal to 1 minus Q2 by Q1, where Q1 is the heat absorbed by the system from a hot reservoir, and Q2 is the heat released by the system to a cold reservoir. If Q2 is equal to 0, then the efficiency of the heat engine is 1 or 100%. Such a heat engine is called a perfect heat engine. This means a perfect heat engine can convert all the heat absorbed into work without any transfer of heat to the cold reservoir. Can a perfect heat engine be constructed? No. Every attempt to construct such a perfect heat engine has failed. In fact, the reason may not be technical. It may be of fundamental nature. For example, if an engine can convert all the heat to work, it need not take heat from a hot reservoir, but it could absorb heat from its surroundings and convert it into work. If that were possible, a car engine could have taken heat from the surroundings and run the vehicle without burning fuel. In fact, the process of converting heat completely into work is consistent with the first law of thermodynamics. But it seems that nature has put a constraint on such processes. There are many such processes that are valid according to the first law of thermodynamics, but which do not take place on their own. For example, if we rub our hands, they become warm. On the other hand, do both the hands absorb heat from their surroundings and rub each other on their own? Consider a metallic box with two chambers separated by a partition. One of the chambers is filled with some gas and the other chamber is empty. If the partition is lifted, we all know that the gas diffuses to the other chamber. Can the diffused gas molecules on their own move back and occupy the first chamber only? That will probably never happen. Some of these processes do not take place because nature does not permit them to. Hence, there must be a law of nature that decides whether a given process, allowed by the first law of thermodynamics, actually takes place or not. The second law of thermodynamics is the principle of nature, which disallows certain processes from taking place even though they are consistent with the first law of thermodynamics. There are many ways to state the second law of thermodynamics. One form of the second law of thermodynamics, which denies the possibility of a perfect heat engine, has been given by Kelvin and Planck. It states that no process whose sole result is to absorb heat from a reservoir and convert it completely into work is possible. There is another version of the second law of thermodynamics, which explains a fundamental limitation to the coefficient of performance of a refrigerator. Earlier, you learned that the coefficient of performance of a refrigerator, alpha, is equal to Q1 by W, where Q1 is the heat extracted from the cold reservoir, and W is the work done on the system. If W is equal to 0, then the coefficient of performance is infinity. This means a refrigerator with a coefficient of performance equal to infinity can extract heat from a cold reservoir and release it to a hot reservoir without any external work on the system. Such a refrigerator is known as a perfect refrigerator. But the second law of thermodynamics places a restriction on this. The other form of the second law of thermodynamics, which restricts the possibility of a perfect refrigerator, is given by Clausius and states that no process is possible whose sole result is the transfer of heat from a colder object to a hotter object. This means we can't make a refrigerator function without any external work on the system. Both ways of stating the second law of thermodynamics are equivalent. Any one form of the law can be logically derived from any other form. Let us assume that the statement given by Clausius is wrong, and there exists a perfect refrigerator that absorbs Q1 heat from a cold reservoir at temperature T2 and releases the same to a hot reservoir at a temperature T1. Let there be a heat engine working between the same two temperatures T1 and T2. Let us also assume that this heat engine absorbs heat energy of Q1 plus Q2 from the hot reservoir, does some work W, and returns heat Q1 to the cold reservoir. If we take the combination of these two, the net effect is the absorption of heat Q2 from the hot reservoir, which is converted completely into work W. We can have a perfect heat engine. That means that if one form of the second law of thermodynamics is violated, and the other form is also violated. The first law of thermodynamics is a statement of the law of conservation of energy, according to which energy can neither be created nor destroyed. Whereas the second law of thermodynamics restricts the availability of energy and the ways in which it can be used and converted. Consider a system taken from its initial state I to a final state F in a thermodynamic process. Let us represent the process in a PV diagram as shown. The process is called a reversible process. If the system and its surroundings can be brought back to the initial states without causing any change anywhere else in the universe. But many natural processes are not reversible. For example, when coal is burnt, it converts to ash and carbon dioxide and in the process releases some heat. Can the process be reversed and convert ash to coal again? We observe accumulation of dust everywhere in our houses. Can the accumulated dust on its own fly away and make the house clean? Not only the processes we have just discussed, but many other processes in nature are not reversible. In fact, we can conclude that irreversibility is not an exception but a rule of nature. Why is it so difficult to find a reversible process in nature? Let us consider a steady flow of liquid through a pipe of variable cross-sectional areas. As the liquid flows through the pipe, it may have different speeds at different points. Let the speed of the liquid at A be V1. When it moves from A to B, its speed increases, say from V1 to V2. The process is reversed and the speed of the liquid decreases from V2 to V1 as it moves from B to C. Hence, the process is almost reversed. The complete reversibility of this process is possible only if the liquid is non-viscous. This means the speed of the liquid is the same at A and C only if the liquid is non-viscous. However, in real life, this does not happen. Because of the dissipative effects due to friction, viscosity, etc., complete reversibility is not possible. As we can only minimize the effects of dissipative forces and cannot completely eliminate them, most processes in nature are irreversible. There is another cause for irreversibility that arises due to the system passing through non-equilibrium states. When the system is passing through non-equilibrium states, we cannot identify the intermediate states of the system precisely. As a result, we can't identify the correct path through which the system has passed, while changing from the initial state I to the final state F. Hence, reversibility of the process is very difficult. However, we have defined a quasi-static process as an ideal process that always passes through equilibrium states. Now, we can write the conditions for a process to be a reversible process. For a process to be reversible, it must be quasi-static. And there must be no dissipative effects. Like a quasi-static process, a reversible process is also an ideal one. For example, consider an ideal gas in a container with a frictionless movable piston. A quasi-static expansion or compression of this gas is an example of a reversible process. According to the second law of thermodynamics, we cannot construct a heat engine with 100% efficiency. So, what is the maximum efficiency of a heat engine? If a heat engine working between two temperatures, T1 and T2, passes through idealized reversible processes, then the heat engine achieves the highest efficiency possible. Much before the concepts of thermodynamics were established, Nicolas Léonard, Sadi Carnot, a French physicist, proposed a hypothetical ideal heat engine that works with maximum possible efficiency. A hypothetical reversible heat engine operating between two temperatures is called a Carnot engine. To get the maximum possible efficiency, all the processes involved in the working of the Carnot engine operating between two temperatures must be reversible. Since all the processes are reversible, there will be no dissipative effects. We know that a process is reversible only when it is quasi-static. In a quasi-static process, the system will always be in thermal and mechanical equilibrium with its surroundings. There are two processes in which a heat engine exchanges heat with the surroundings. In one process, the heat engine absorbs heat from a hot reservoir at temperature T1. And in the other process, it releases heat to a cooled reservoir at temperature T2. Since the system must be in thermal equilibrium, these two processes need to be isothermal. There must be two more processes. In the first process, the temperature of the system changes from T1 to T2. And in the other process, the system is taken back from T2 to T1. Since there is no exchange of heat involved in these two processes, they must be adiabatic. The cycle of two isothermal and two adiabatic processes through which the working substance of a Carnot engine passes is known as the Carnot cycle. Let us now discuss the sequence of steps involved in each Carnot cycle. Consider mu moles of an ideal gas in a container with a movable, airtight, smooth, frictionless piston as the working substance. Let the walls of the container and the piston be made of thermally insulated material, and the bottom of the container be made of diathermic material. Assume that the initial state of the system is P1, V1, T1 and is identified by point A in the PV diagram. Note that the gas is in a compressed state because of some tiny weights on the piston. In the first step, place the container on a hot reservoir, which is at a constant temperature T1, and slowly remove some of the tiny weights one after the other, and allow the gas to expand isothermally. During this expansion, let the state of the gas change to P2, V2, T1, which is identified by point B in the PV diagram. Let the heat absorbed by the gas be QAB and the work done by the gas be WAB. For an isothermal process, there is no change in the temperature of the system, and hence the change in the internal energy is zero. Therefore, the heat absorbed by the system is equal to the work done by it. Therefore, for an isothermal process, the work done by the system WAB is equal to mu R T1 ln V2 by V1. Let this be equation 1. In the next step, the container is kept on an adiabatic platform. Now, by removing some more tiny weights, one by one, allow the gas to expand. Since the gas is surrounded by adiabatic material, there can be no exchange of heat between the system and its surroundings, and hence the expansion is an adiabatic expansion. Let us assume that this adiabatic expansion has taken the system from B P2 V2 T1 to C P3 V3 T2, and that this is represented by the BC curve in the PV diagram. For an adiabatic process, heat absorbed QBC is equal to 0 and the work done WBC is equal to mu R into T1 minus T2 by gamma minus 1. Let this be equation 2. Since for an adiabatic process, Tv to the power of gamma minus 1 is constant, we can write T1 V2 to the power of gamma minus 1 is equal to T2 V3 to the power of gamma minus 1. Let this be equation 3. In the next step, let us place the container on a cold reservoir, which is at temperature T2. By placing back some of the tiny weights on the piston, allow the gas to compress isothermally. In this process, the system releases heat to the cold reservoir. Assume that during the process, the state of the system is taken from C P3V3T2 to D P4V4T2. Let the heat given out by the system to the cold reservoir be QCT, and the work done on the system be WCT. Since the process is isothermal, QCD is equal to WCT, which is equal to mu RT2 ln V3 by V4. Let this be equation 4. In the final step, place the container on an adiabatic platform once again and compress the gas by adding small weights one by one. This adiabatic compression has taken the state of the gas from dP4V4T2 to AP1V1T1. The work done on the system, WdA, is equal to mu R into T1 minus T2 by gamma minus 1. Let this be equation 5. As the process is adiabatic, we can write T2V4 to the power of gamma minus 1 is equal to T1V1 to the power of gamma minus 1. Let this be equation 6. In one complete cycle, the work done by the gas W is equal to WAB plus WBC minus WCD minus WDA. Note that we have taken the negative sign for WCD and WDA as the work is done on the system during the compression. On substituting the values from equations 1, 2, 4 and 5, we get W is equal to mu RT1 into ln of V2 by V1 plus mu R into T1 minus T2 by gamma minus 1 minus mu RT2 into ln of V3 by V4 minus mu R into T1 minus T2 by gamma minus 1. On simplification, we get W is equal to mu RT1 into ln of V2 by V1 minus mu RT2 into ln of V3 by V4. Let this be equation 7. We know that the efficiency of the heat engine, eta, is equal to the ratio of the work done by the system to the heat absorbed by the system. The total work done is W, and the total heat absorbed is QAB. Note that heat is absorbed only during the process AB. In processes BC and DA, no heat is exchanged since they are adiabatic. And in process CD, heat is released. Hence, these three processes are not considered. Therefore, efficiency is equal to W by QAB. Substituting the values for W and QAB from equations 7 and 1, and on further simplification, we have eta is equal to 1 minus T2 by T1 into ln of V3 divided by V4 by ln of V2 by V1. Let this be equation 8. Equation 3 can be rewritten as V2 by V3 is equal to T2 by T1 to the power of 1 by gamma minus 1. Let this be equation 9. Similarly, equation 6 can be rewritten as V1 by V4 is equal to T2 by T1 to the power of 1 by gamma minus 1. Let this be equation 10. From equations 9 and 10, we have V3 by V4 is equal to V2 by V1. Let this be equation 11. From equations 8 and 11, we get eta is equal to 1 minus T2 by T1. Let this be equation 12. Hence, the efficiency of the Carnot engine eta is equal to 1 minus T2 by T1. We know that the Carnot cycle is a reversible cycle. Every process of the cycle is a reversible process. If each step of the Carnot cycle is reversed, we get a reversible refrigerator that receives QCD heat from a cold reservoir at a temperature of T2, and after work W is done on the system. It releases heat of QAB to the hot reservoir at a temperature T1. Let us now compare the efficiencies of two heat engines working between the same temperatures T1 and T2. One of the engines is an irreversible engine I, with an efficiency eta I, and the other engine is a reversible Carnot engine R, with an efficiency eta R. Let us start with the assumption that the efficiency of the irreversible engine is greater than the efficiency of the Carnot engine. This means eta I is greater than eta R. Let this be expression 1. If eta I is greater than eta R, then the work done by the engine I must be greater than the work done by the engine R. If Wi is the work done by the engine I, and Wr is the work done by the engine R, then Wi is greater than Wr. Let us call this expression 2. Now, let us couple both the engines, such that the irreversible engine I works as a heat engine, and the Carnot engine R works as a refrigerator. Since the Carnot engine is working as refrigerator, Wr is the work done on the system, Let us assume that the heat engine receives heat Q1 from the hot reservoir and returns some heat Q1 minus Wi to the cold reservoir. Let us also assume that the engine R, which is working as a refrigerator, absorbs heat Q2 from the cold reservoir and returns heat Q1 to the hot reservoir. Then the work done on the engine R, WR, must be equal to Q1 minus Q2. This also implies that Q2 is equal to Q1 minus WR. But as per expression 2, we know that WI is greater than WR. Then we can conclude that Q1 minus Wi is less than Q1 minus WR. But Q1 minus Wi is the heat returned to the cold reservoir by the engine I. And Q1 minus WR is the heat received by the refrigerator. Substituting the value of Q2 in this expression, we get Q1 minus Wi is less than Q2. Since Q2 is greater than Q1 minus Wi, the net heat taken from the cold reservoir is Q2 minus of Q1 minus Wi. On substituting the values of Q2 and on further simplification, the net heat taken out of the cold reservoir is equal to Wi minus WR. Note that the coupled system has received Q1 heat from the hot reservoir and has returned the same heat to the hot reservoir. This means the coupled system is able to extract net heat from the cold reservoir and convert it completely into work. This is a violation of the second law of thermodynamics. This means our earlier assumption that eta I is greater than eta R, or the irreversible engine is more efficient than the reversible Carnot engine, is wrong. This conclusion leads us to Carnot's theorem. It states that working between a given set of temperatures, no engine can have an efficiency greater than that of the Carnot engine. It also states that the efficiency of the Carnot engine is independent of the nature of the working substance. Though we use the ideal gas equation while deriving equation 12, it must be true for any working substance. If we compare equation 12 with the equation eta is equal to 1 minus Q2 by Q1, we get Q2 by Q1 is equal to T2 by T1. Note that this relationship Q2 by Q1 is equal to T2 by T1 is a universal relationship and is independent of the nature of the system.